In part B of our measurement lab, things are going to be a little bit different. In part B, we're still comparing radius to something, but instead of it being the circumference, we're comparing radius of our circles to the area of the circles. All right, so let's go ahead and right away start by setting up our data table. Now, this could be an extension of what you have done already in part A, but since I'm working on a different slide right here, I'm going to write down radius again. And if you're dealing with the same circles, which you should be, you already have radius written down anyway. So radius 1, radius 2, radius 3, radius 4, and radius 5. And so you've measured that, and that. I'm not going to bother writing in the R1, 2, 3, and 4, and 5. But what we're going to be comparing it to, though, is now area. Oh, by the way, I should remind us that this is centimeters right there, because the radius is a length. It's the distance. We're going to be comparing this to area. But as you know, that an area is a length by a length. That is height by width, or width by depth, or whatever you want to call it. And so it would be centimeters, fix that, squared. This is not happy today. Centimeters squared. Okay? You measure area 1, area 2, area 3, area 4, and area 5. Right now you're saying to me, whoa, Mr. Mounts, how exactly do we measure these areas over here? Well, the reason that we plotted them on graph paper is because it makes it convenient to count blocks. I know you probably know some sort of relationship between the radius and the area of a circle, but I don't want you to use a calculator. I want you to measure it physically. And so the easiest way probably for us to do this is simply, I'm going to zoom in here a little bit, is to simply count blocks. Now, the smaller the blocks, the better this works out, because I want you to count full blocks. There's 1, there's 2, there's 3, there's 4. And again, this is why I said it's okay if the circles overlap, because as long as you count them right, as long as you are okay with these overlapping right here, and don't lose track, it's perfectly fine if they overlap. You're just counting blocks at 2 different times. So 5, 6, 7, 8, all these full blocks right here. If you want to be really nitpicky, you can maybe say you'll also count half blocks as well, like this one right here. But when you get down into quarter blocks and little corners like this, it's like where do you draw the line? I would recommend, for the sake of simplicity, just counting whole blocks. It's going to lead to a little bit of error, but that's okay. We can account for that. So count the number of whole blocks, and it's very possible that you will be using you'll be using half centimeter graph paper. All right, so that is a half a centimeter, and that is a half a centimeter right there, and so that would be a half a centimeter block. But remember, you measured radius in centimeters, and we want to keep our measurements or our units the same. So even though you are counting it in half centimeter blocks, remember, if we're measuring in full centimeters, there are 4 half centimeter blocks in 1 whole centimeter right here. I don't want that to mix you up too much, but we're going to make a conversion a little bit later on. So we convert 0.5 centimeters squared. All right. We're going to convert that to how many centimeters squared. All right, or I should probably turn that around. Well, you see that there's 4 of these for every 1 of these, so that coefficient out in front. Where's my eraser? There it is. This coefficient out in front right here, which I somehow, for some reason, can't erase. This question mark, is going to turn into a 1 over 4. All right, sorry about that. That is this right here, this little guy, is 1/4 of what a whole square centimeter is. That's important to know because it's nice to have small blocks so we can count them up, but we really want to convert later on to full square centimeters. And so what you may want to do is make another data column for full square centimeters and then make your conversion a little bit later on. I can help you with that. But for now, we're just going to be counting these blocks right here. So 1, 2, 3, 4, 5, 6, 7, 9, 10, 11, 12, 13, 14, and so forth. So count the number of whole blocks. This is going to be area 1, area 2, and so forth. All right, I'm going to zoom back out right here so we can see everything. And again, like before, we are going to plot the x and an x and y chart by hand on our graph paper. Those lines aren't too bad. All right. Once again, on the x-axis, in fact, let me back up for a second. I'm going to erase this. I'm going to make two x-y axes right here. All right. Because we're going to find something interesting happen here. And we plot radius versus area. So I'm just going to make this r. That's going to be in centimeters. And area, I'll just put capital A right here. You're going to convert these little guys over here to centimeters cubed. All right, so you're ultimately going to have an area in centimeters cubed. Centimeters squared. You're going to have it in centimeters squared, not half centimeters squared. So cm squared, right there. And you're going to plot them. Let me get I'll do blue again. All right. What you're going to find is that there is no slope of this line because the slope keeps changing. It's not going to be a line at all. It's going to be a curve. It's going to be a curved line. So if we ask ourselves, what is the m here? What's the relationship between the radius and the area? There is no direct relationship between the radius and the area because it keeps changing. It keeps changing. It's not linear at all. It's this curved line. Think about it for a second. We have centimeters squared on the y-axis. We've got centimeters, regular old centimeters on the x-axis. Those aren't the same, and so we're going to have this kind of skewed, bent graph right here. So I'm going to suggest us doing something that's called linearization. I'm going to ask us to put r, that is the radius column, squared. All right? So our r values, I'm going to ask us to square that and put that on the x-axis and compare that to our centimeters squared on the y-axis. The reason I'm asking us to do that is, we'll find out a little bit later, but in your second graph that you do, take this r value right here and square it. So you'll probably need to create another data column as well. So whatever your r1 is, you're going to have to square it down here. So r1 squared, r2 squared, r3 squared, r4 squared. Plot that against your regular old area, which is already in square centimeters. And I think you'll find, and know you'll find, that you're going to get a nice linear relationship. This is what's called linearization. And when we talk a little more in class, in lab class, about the relationship between radius and area, you may know the relationship between radius and area from math. It makes sense why if we square the radius, we'll have a nice m. Oop, that isn't a nice m. We'll have a nice m value that you can measure. You can take your rise over your run and get your slope right there. We'll talk more about that at length in class with my horrible X or question mark right there. But for the second part, for part B, you're going to want to draw a regular nonlinear or a regular graph of radius versus area. It'll be curved. And then I'm going to ask for the second graph. The difference is you're going to take your R values and square them. Plot that against your area, and you'll get a straight line and a curve right there. We'll talk later about what those, a slope right there. We'll talk later about what the slopes actually mean, but this gives you a heads up as to what to do in class so you're not lost. So hopefully that helps, and I'll see you in lab.